In this video, we're going to go over the Robinson annulation reaction. And so here we have cyclohexanone, and we're going to react with a base. Let's start with hydroxide. And so hydroxide is going to remove the alpha hydrogen, giving us an enolate ion. Now, in the next step, we're going to react the enolate ion with this molecule, an alpha beta unsaturated ketone. So here's the alpha carbon, this is the beta carbon. And so this step is a Michael reaction. This is the Michael donor, it's the nucleophile, and the Michael acceptor is the electrophile. Now, it's important to understand that the Michael donor, in this case the enolate ion, it can attack at the beta carbon, giving us the Michael reaction, or it can attack at the electrophilic carbonyl group. But in this video, we're going to focus on the attack at the beta carbon, which will lead us to the Robinson annulation reaction. So once the enolate ion attacks the beta carbon, then these pi electrons will move here, causing the pi bond between the carbon and the oxygen to break. And so we're going to get a structure that looks like this. So we still have the ketone, and then we're adding 4 carbons. Here's the beta carbon, the alpha carbon, the carbonyl carbon, and right now we have an oxygen with a negative charge, and there's another methyl group attached to it. So the double bond is between the carbonyl carbon and the alpha carbon. So now in the next step, we're going to react this with water. When hydroxide took a hydrogen, it turned into water. And so the oxygen with a negative charge is going to use one of its 3 lone pairs to form a pi bond, causing those pi electrons in that carbon-carbon bond to grab a hydrogen, regenerating the hydroxide ion. And so right now, we have this. We have a ketone with a methyl group, and there's another ketone here. Now, we can remove an alpha hydrogen on this side of the ketone, because if we do, the ring will close, forming a 6-membered ring. Whereas if we take off the alpha hydrogen here, if it attacks here, it's going to form an unstable 4-membered ring. And 6-membered rings are more stable than 4-membered rings. And so a cyclohexane ring has 0 ring strain. Therefore, we are going to remove this hydrogen with hydroxide. And so that's going to give us another enolate ion, which we can draw here. And so now we have a negative charge on this carbon, and then that carbon can attack the carbonyl carbon, causing that pi bond to break. And so the Robinson annulation reaction, it forms 6-membered rings. The first step is a Michael reaction, and the Michael reaction produces 1,5-dicarbonyl products. And then this second step that we're doing now is actually an intramolecular aldol reaction. So right now we're going to get an oxygen with a negative charge. We have another 6-membered ring, and here's the ketone. So the next step is protonation. So the alkoxide ion is going to take a hydrogen from water, regenerating hydroxide. So now we have an OH group. Now, in the next step, we need to use that regenerated hydroxide ion, or any hydroxide ion in a solution, to basically dehydrate the alcohol. And so for this step, in order to remove water, we need to heat it. By heating the solution, we can drive water out of the solution, thus taking this reaction and driving it to the right. So once you heat the solution, hydroxide is going to take away the alpha hydrogen, forming another enolate ion. And then the next step, we can use the enolate ion to eliminate the OH group. So we're going to take this lone pair, form a pi bond, and then expel the hydroxyl group. And so now we have our final product, which looks like this. And so that is the Robertson annulation reaction. It forms rings, and it's basically a microreaction with an intramolecular aldol reaction. Now let's work on another example. So let's react acetone with this alpha beta unsaturated ketone under basic conditions. So draw the Robertson annulation product that can occur in this reaction. Feel free to pause the video and work on that problem. So let's start with the ketone. So the first step is the use of a strong base to remove the alpha hydrogen. Now once we have the enolate ion, we can react it with the alpha beta unsaturated ketone. So the enolate ion, it's going to attack the beta carbon of this compound, causing these pi electrons to move here, breaking the pi bond between the carbon and the oxygen. And so let's call this carbon 1, 2, 3, 4, 5, 6, and 7. So we're going to have a 7 carbon chain, which looks like this. So this is 1, 2, 3, 4, and so forth. Now on carbon 6, we have an oxygen with a negative charge. And between carbons 5 and 6, we have a double bond. So now we need to react that enolate ion with water. So the oxygen is going to use one of its lone pairs to form a pi bond, causing carbon 5 to extract a hydrogen from water. And so what we have right now is a 1,5 dicarbonyl compound, which is the typical product of a microreaction. So now let's move on to the intramolecular aldol reaction. So the next step is to take the hydroxide ion, remove a hydrogen, and form the enolate ion. And then we're going to take the carbon with the negative charge and use it to attack the other carbonyl carbon. And so this is going to be carbon 1, 2, 3, 4, 5, 6. And so we're going to get a 6-membered ring. So now we're going to say that this is carbon 2. And here this is carbon 1. This is 3, 4, 5, and 6. So at 2 we have a ketone. At carbon 6 we have an oxygen with a negative charge, and we also have a methyl group. So now let's protonate the alkoxide ion. So this oxygen is going to grab a hydrogen from water, regenerating the hydroxide ion. And so the product that we have right now is called a beta hydroxy ketone. So here is the alpha carbon, here's the beta carbon. And so we have a hydroxyl group on a beta carbon. So that's a beta hydroxy ketone. Now in the next step, we need to remove the alpha hydrogen. Giving us the enolate ion again. Now for this step, keep in mind that we need to remove water. And so this is the dehydration step. And we need to use heat in order to facilitate the removal of the hydroxyl group. And so now we can take the negative charge of the carbon, take that lone pair, form a pi bond, and kick out the hydroxyl group. And so this is our product for the Robertson annulation reaction. So we have a cyclic alpha beta unsaturated ketone. Let's go over one more example. So go ahead and predict the major product between these two. Go ahead and try that. And we're using the base, of course. Now, this particular Michael donor is better than the other one because once we form an enolate ion, that enolate ion is stabilized by two carbonyl groups. And so this is a weaker base, which means that it's going to more likely attack the beta carbon as opposed to the carbonyl carbon. Strong bases prefer to attack at the carbonyl carbon, but weaker bases, they prefer to attack at the beta carbon, favoring the Michael reaction. And so an enolate with two carbonyl groups is a better Michael donor than an enolate with one carbonyl group. So like in the last example, we use this as an enolate. And so this particular enolate can attack at the beta carbon or at the carbonyl carbon because it's a stronger base. However, this one is a weaker base, and so we're going to get a much greater yield of the product that's produced when it attacks the beta carbon. And so just keep that in mind. This is a better Michael donor than this one. So this one favors conjugate addition where it attacks the beta carbon. And this one, it can attack at the beta carbon given the conjugate addition product, or it can attack at the carbonyl carbon given the direct addition product. So just keep that in mind, but we're going to focus on the reactions that lead to the conjugate addition product. So the first step is going to be deprotonation, as always. So once we remove the alpha hydrogen, we're going to get this enolate ion, which is going to attack the beta carbon, causing these electrons to move here. And so we're going to get this intermediate. So this is the beta carbon, the alpha carbon, the carbonyl carbon, and the methyl group. And we have a double bond between the alpha carbon and the carbonyl carbon. So the next step is going to be protonation. So this oxygen is going to reform the pi bond, causing these pi electrons to bond with the hydrogen. So this hydrogen goes to the alpha carbon. So now we have a double bond O. And let's see, we also have another double bond O here. Now the next step is to take off the alpha hydrogen. Giving us another enolate ion. And so the enolate ion is going to attack the carbonyl carbon, and so it's going to close and form another ring. So we have an oxygen with a negative charge at this point. And so we're going to react that with water. And keep in mind, there is another ketone molecule over here. So our next step is another deprotonation reaction, but this time we need to use heat to favor dehydration. And then the final step is the removal of the hydroxyl group. And so this is it. This is the Robeson annulation product for this reaction. And so now we have a double bond in this region. So that's the final answer. Now I want to review direct addition and conjugate addition because it's relevant to this reaction. So what you need to understand is that weak bases, when they behave as nucleophiles, they prefer to attack the beta carbon. And so they favor conjugate addition. Now, if you have a strong base, when it behaves as a nucleophile, it prefers to attack at the carbonyl carbon, favoring direct addition. And so strong bases that do this would be like the Grignard reagent. Weak bases that favor conjugate addition will be like cyanide. Now keep in mind the pKa for cyanic acid is about 9. Now bases like sodium borohydride, it can do both. For this alpha beta unsaturated aldehyde, it could do direct addition and it could do conjugate addition, so you get a mixture of products. But the basic idea is that strong bases, they favor direct addition, weak bases favor conjugate addition. Now in this video we use a ketone as a Michael donor, and we also use a diketone as well. The pKa for water is about 15.7. For the alpha hydrogen of a ketone, it's about 20. And for the alpha hydrogen of a diketone, it's 9. So therefore, we could say that the enolate ion is a stronger base than hydroxide, which is stronger than the enolate ion that's between two carbonyl groups. So relative to hydroxide, this is considered to be a weak base, and this is considered to be a strong base. Now let's say if we wish to compare these two Michael donors with an alpha beta unsaturated aldehyde. Now, because this is a weak base, this is going to favor conjugate addition over direct addition. Now, this is a stronger base, so it's going to favor direct addition. Now, this could do both. It can still attack here, so keep that in mind. You can get both products. However, this is going to give you a better yield for the Michael reaction, which will lead to a better yield for the Robeson annulation reaction. So just remember that weak bases, they favor conjugate addition, attack at the beta carbon, and strong bases, they favor direct addition, attack at the carbonyl carbon. So that's the first thing you need to look at when deciding where the Michael donor or the nucleophile is going to attack. The second thing is the Michael acceptor or the electrophile. Let's compare an aldehyde with a ketone. Because in this video, we were using ketones as opposed to alpha beta unsaturated aldehydes. Now, which carbonyl group is more electrophilic or more accessible towards nucleophilic attack? Aldehydes are more reactive than ketones. This is because the carbonyl group of an aldehyde is more accessible than the carbonyl group of a ketone. The CH3 provides some steric hindrance to this carbonyl group. At the same time, it's an electron donating group, so it makes this carbonyl group less electrophilic. And so it's easier for the enolate ion to attack the carbonyl carbon of an aldehyde, but it's more difficult to attack the carbonyl carbon of a ketone. So for this particular enolate ion, we're going to get a better yield for the Michael reaction and a Robeson annulation reaction. It's easier for it to attack the more accessible beta carbon. And that's what we had in this example. We can increase the yield even further by making this carbon more sterically hindered, or making it more bulkier, which means that this carbonyl group is basically blocked from a nucleophilic attack. And so that will increase the yield of the conjugate addition product. So there's two things you need to look at: the strength of the base that you're using, and also the accessibility of the carbonyl group. If it's accessible, then a strong base is going to attack here. If it's not accessible, both the strong base and the weak base will attack at the beta carbon.